Hey, welcome back to the third video on log functions. What we did previously was we looked at using log rules to expand expressions involving logs. Now we'll look at using log rules to combine expressions. In a sense, it's like I don't want to say, I take it back. It's not like factoring them, but it's unexpanding them. So the rule they're going to use for this first one, the log functions, they have the same base, they're both base e. The rule I'm going to use is the log of m times n is equal to log of m plus log of n. Just using that rule in reverse now. I'm putting them together as the log of one of them times the other one. So this becomes the ln of x minus 5 times x plus 5. Which, if you're interested, you could expand. You could FOIL this out as x squared minus 25. The cross terms cancel. Okay, next. I'm going to go with the one on the right, and we're going to use two rules. We have the log of m times n rule and the log of m divided by n rule. We're going to use both rules together. We have the ln of the top thing for, put some brackets to make sure I don't screw everything up, 4x minus 18. Then we have a subtraction, ln, so minus ln of something, so divide by 2x plus 6. And then we're plus ln of x, so that goes on top. Like that. And that's good. I won't bother expanding it or doing anything else to it. And I'll circle both of these. I'll put or. They're both good final answers. All right, the next ones are a little bit more challenging because we can't immediately do what we just did. What we have to do first is that this rule, this log of m plus log of n is log of m times n, that rule is for nothing being in front of the log functions. And this example on the bottom left, we currently have a 2 in front of the first one and a 3 in front of the second one. We got to get rid of those. Fortunately, we have a way to get rid of those. We can bring them up as powers. So we're going to use the rule log of m to the power of n is equal to n times log of m. We're going to use that rule in reverse. We're going to take the n that's in front and bring it up as a power. So this is the ln of x plus 1 to the power of 2 plus the ln of x to the power of 3, bringing those powers up. Now I'm going to use the log property, log of m plus log of n is equal to log of m times n. Uh-oh, don't zoom, please. Oh, stop doing this. Okay. So this is going to be the log of x plus 1 all squared times x cubed. And I'd say that's a good answer. Don't mess with it. Don't start expanding. Don't start foiling and doing weird stuff. All right, and then the last one, I'm going to start by making sure that those constants in front are brought up as powers to give us access to the other log properties, the log of m plus, or in this case, log of m minus n property. So we're going to say log of m to the power of n is equal to n times log of m. We're just using it in reverse. So we have the ln of the square root of x squared plus 4x minus the ln of x minus 1 all squared. Common question at this point is, can I bring up the negative as well? So I get plus the ln of x minus 1 to the power of negative 2, and my answer is yes, that's allowed, and it will give you the same result. Okay, next step, working on what we have here, I'm going to use this rule in reverse, log of m, need some more space, log of m minus log of n is the log of m divided by n. So we're going to have the log of the first divided by the second, ln of x squared plus 4x divided by x minus 1 all squared. And a really good question to ask is which one are we supposed to do? Are we supposed to expand things like we were in the previous examples, or are we supposed to collect things and condense them and simplify them like we are here? And the answer to that is it depends on what we're trying to do. It depends on what comes next, like what's the goal of the calculation. This is not familiar territory for, I'd say, anyone. Most people don't like log functions, and most people have not had adequate exposure to them to not hate logs. There's common mistakes that are made when working with log functions. One of them is that if you have a log of a top thing over a bottom thing, instead of correctly dealing with that and saying it's a log of the top minus the log of the bottom, one of the temptations you will have, but all of us have at some point, is to say it's the log of the top divided by the log of the bottom, which it's not. You cannot distribute the log operation to the top and bottom separately. The only way to distribute, quote unquote distribute it, is through subtraction, not by division. Likewise, if you have the log of two things added together and you leave it alone, you're doing something good. You're not supposed to split it up. Like, you could not say that the log of a plus b is equal to log of a plus the log of b. You cannot say that the log of x squared plus x cubed is equal to the log of x squared plus the log of x cubed. And it doesn't matter what the base is. It's just never true. Be on the lookout for these two types of errors. And marking over the years, these are the two most likely errors that you're going to make when working with log functions and working with expressions involving logs. Now, until this point, I've just been treating logs as these functions that have rules. But we can plug numbers into them, make a table of values, and graph them. So shown here and at the top picture is the graph of 10 to the power of x, so if I was about to write it in, so that's 10 to the x in red, and the graph of log base 10 of x in blue. Well, what do you notice? Those of you who've taken art. Maybe if you haven't taken art, you'll notice it anyway. But if you draw this line, y equals x, what do you see? You see a mirror reflection. That 10 to the x is a mirror reflection of log base 10 of x. They're mirror images of each other about the line y equals x. If you put a mirror there, you would see that image in the mirror. Mirror going up and down, like resting on the page. On the bottom picture is a graph of several log functions graphed together. We have log function with a base of 2, log function with a base of e, so ln, one of them that's in red, and log function with a base of 4. Notice that the larger the base of the log function, the more slowly it grows. So it's like the opposite of an exponential. An exponential function with a large base grows very quickly compared to an exponential with a small base. Now, the good thing is that the log function with a base of e is in between the log function with a base of 2 and log function with a base of 4. Because e is between 2 and 4. It's actually between 2 and 3. All these graphs touch, all these log graphs touch at 1, 0. And why is that? Because the log of 1 is 0. 1 is the x value, 0 is the y value, because log of 1 equals 0 for any base, for any log base. So that's where they all cross. We've already seen previously that one of the most powerful ways to work with exponential functions and log functions is through the cancellation laws. And I don't even have the language cancellation law here, and I should add it. So these are the cancellation laws in both directions. B to the power of log base b of x is equal to x, and log base b of b to the x is equal to x. The top rule has a restriction. It's only true for x positive, and that's because you can't plug a negative number into a log function. Whereas the second order of the cancellation law that has no such restriction because you're not plugging x into a log function. You're plugging x into an exponential first. That will make sure that as long as the base of the exponential function is positive, which is a requirement, that'll make sure that the argument that's being plugged into the log function is positive. So we don't have any domain problems for the second order, but we do have a potential domain problem for the first one. These are the same cancellation laws. They're exactly the same as the ones in the previous slide, except they're using ln instead of log. But ln is log. It's a log with one particular base instead of log with a general base. So in the next set of examples, we're going to be solving for x as trapped in a log function, and we're going to be thinking about our log rules and the cancellation law. We're going to use them together. General strategy. Isolate for the exponential part of the expression. So in this case, this means e to the x plus 5. So we want to isolate for that first. You'll see why in a moment. So I'm going to divide both sides by 7. E to the x plus 5 is equal to 3 divided by 7. Now in the next step, I'm going to use the cancellation law. How do we use a cancellation law? This is a new operation. We've never done this yet. I listed it as one of the new operations, but we never had cause to use it. We're going to log both sides. Choose any base. Now we can choose any base, but one base is better. Choose any base, so I'll cross that out. We can do it. It is best to use the same base as the exponential function containing x. So here's how we do that. I'm going to take the long left side. So that means take ln of both sides, since ln is log base e. So I take the ln of the left side and the ln of the right side. So the ln of the left equals the ln of the right. Ln of e to the x plus 5 equals the ln of 3 over 7. On the left side, we have a cancellation law. So x plus 5 equals the ln of 3 over 7. All right, looks weird, right? Looks like now my answer is bizarre. It's ln 3 over 7. What am I supposed to do? Remember, the goal is to get x all by itself. Right now we have x plus 5. And think about those operations that we're allowed to do. Multiply both sides, divide both sides, subtract from both sides, add from both sides. Those operations are still here, even though we have exponentials and logs. Like they haven't gone anywhere. So the next thing I'm going to do is I'm going to subtract 5 from both sides to accomplish the mission, which is to get x all by itself. So x is ln 3 over 7 minus 5. And that's it. That's our answer. We don't mess with it. That is the exact answer. It is not a pretty answer. It is not a nice number. Ln 3 over 7 is a weird decimal. note. I should add that. I should say note. Ln of 3 over 7 is some decimal number. Okay, let's do another one. Oh no, now we have, so the previous one we had x trapped in an exponential function, and to untrap it we had to log both sides. And this one we have x trapped in a log function. And logging both sides is not going to be part of our agenda. You'll see what we have to do. So first step is isolate for the log part of the expression that contains x. So I'm going to start by subtracting 2 from both sides. I have 2 times ln of x is equal to 8 minus 2. So 2 ln of x is equal to 6. Then I'm going to divide both sides by 2. So ln of x is equal to 6 divided by 2. So ln of x is equal to 3. And the next step, I'm going to exponentiate both sides. As powers on a base of what? What base do we use? We exponentiate both sides, and we're doing this to get access to the cancellation law. This log function that we have is a log function with the base of e. So we're going to exponentiate with a base of e to match the base of the log function and access the cancellation law. So I'm going to raise both sides. E to the power of the left side is equal to e to the power of the right side. So e to the power of ln of x equals e to the power of 3. I have a cancellation law here. And I get my answer, x equals e to the power of 3. And that is the answer. 2.71828 ... raised to the power of 3. That's the number that x must be equal to. All right. This deserves a break. See you in the next video.